Professor Jim Wild, actually of Lancaster University, nicely enough, to give us the James Dungey lecture for this year. Title is Space Weather, Living with Our Star. Jim.
So good afternoon, everybody. It's an absolute pleasure to be here this afternoon, and I should thank the President and the Society for awarding this prize lecture. It's a real honour to come and give this. And so for this afternoon, I thought I'd come and talk about space weather, because I think it's an interesting and quite a relevant issue, and it bridges nicely, I hope, between astronomy and geophysics. So it should be something for everyone in this. So we'll begin with thinking about what is space weather. And a good place to go, it's got the name weather in the title. So if we go and have a look at the World Meteorological Organization and we see what their definition is, you can see it behind me. Space weather encompasses the conditions and processes occurring in space, including on the sun, in the magnetosphere, ionosphere and thermosphere, which have the potential to affect the near-Earth environment. So what does that mean? Well, by the time I get to the end of this lecture, hopefully you'll have an idea of some of the ways it can impact on our everyday lives. But one of the most obvious impacts of space weather on the Earth, which has been around for a very long time, even longer than the Royal Astronomical Society, is, of course, the Northern Lights, the Aurora Borealis. And so we have some fantastic time-lapse photography of the Aurora Borealis here in northern Scandinavia. And so what we're seeing when we see these fabulous displays of light in the Arctic sky are the photons being released by excited atmospheric gases. So in the case of the green light you're seeing here, this is atomic oxygen at an altitude of between 1 and 200 kilometers above the surface of the Earth. And that oxygen is being excited by the impact of material raining down the Earth's magnetic field into the upper atmosphere. And so the process causes an exchange of energy from the incoming particle to the atmospheric constituents, which then release that, and the colour of the light you get, obviously, is rather dependent on the internal structure of that atom. Well, of course, the Northern Lights have been around for a very long time, and there's a whole lecture on the myths and the legends of the Northern Lights and what people for millennia thought they were seeing here. But scientists have been having a crack at what the Northern Lights are for thousands of years as well. And really, I'm going to start our story relatively recently with this gentleman, Kristian Birkeland. And so we could, again, have a whole lecture series on the history of the study of, the study of the Northern Lights and the space plasma environment. But Kristian Birkeland made quite a few key breakthroughs, and you see him here at the beginning of the 20th century in his laboratory at what is now the University of Oslo. And he had observed on expeditions into the high Arctic how magnetometers, so sensitive magnetic field measuring equipment, would become disturbed when the Northern Lights were out. And he surmised that this must be an electromagnetic effect that was causing a disturbance to the relatively steady magnetic field of the Earth, which we experience at ground level. And so he went back to his laboratory and devised some experiments, and what you're seeing here is one of his terrella, which means little Earth. And what looks like a large fish tank is basically a large fish tank. It's about it's a vacuum chamber with glass walls up to about 5 centimeters thick, from which you could evacuate most of the atmosphere inside. And then you'll see, I'll try and highlight, in the center there is a globe. So there is a conducting sphere that represents, in this case, a planet, the Earth. And inside that there is a coil, a solenoid, with which Birkeland was able to create a magnetic field, so a dipolar magnetic field, not entirely unlike the Earth's. And then, as you'll get from the clue from this large pile of batteries on the right-hand side, he would then pass a very high voltage, high current, through this gas. And the sphere inside, which was magnetized, I've already said, was actually covered with a phosphorescent paint as well. And what he found is, as he adjusted the electrical currents, so got the magnetic field so it looked vaguely like the Earth's, you tended to get the most illumination in the polar regions. And he surmised, therefore, that the Northern Lights were most probably an atmospheric effect, and they were being caused by electrically charged particles carrying current from the space environments into the upper atmosphere. And really, he was bang on the money there, and this was really the birth of space physics. He was an interesting fella, Kristian Birkeland. There was a whole lecture on Kristian Birkeland. Very interesting chap, very, very clever, rather eccentric. You'll notice here he's actually wearing a fez. He used to tell people who asked him what it was for. He would say he would get headaches, and he would occasionally say it was because he was bald, it would keep his head warm. But he would tell some people that it was so that it would protect him from the dangerous radiation given off by the machine. So this is early health and safety at work here. But actually, in terms of health and safety, his laboratory was famous for being full of loud bangs and flashes and funny smells. And quite a few visitors were electrocuted, but not seriously hurt. And so the University Inspection Committee was actually supposed to check all rooms at least once a year, but they never dared enter Birkeland's laboratory. So. And it was rumoured, he did say that if his assistants misbehave, then he puts them inside the Torella. So there's a whole series of anecdotes about Kristian Birkeland. But if we fast forward then from the beginning of the 20th century into the 1930s, this is adapted from a drawing by Chapman and Ferrero, who were considering the interaction of the space environment and the Earth. And at that time, predating the space age, the idea of a constant, steady solar wind had not been developed. And so the thought was that occasionally if the sun was very active, it might, some eruption, basically the sun would belch out a load of material into the space environment. And when it arrived at the Earth, it would be diverted around the planet a bit like the water flowing around a rock in the river. And so you see these sort of streamlines set up. And this was a view that pervaded for a little while, and if we make a complete nightmare of history and just keep taking very large steps forward, if we fast forward to sort of the end of the 1950s, so the beginning of the space race, and so this is February 1958, and the Americans have launched their first successful satellite, Explorer 1. So this was launched on the 1st of February 1958, bearing in mind that Sputnik was launched on the 4th of October the previous year. So this is the Americans in second place in the space race at the moment. And this lineup of proud people here there's two people we should really point out. They're holding aloft a model of Explorer 1. The chap in the centre is James Van Allen of the University of Iowa, who we'll come back to in a moment. And then on his left, this very happy gentleman is Wernher von Braun, obviously of a rocketry legend, but also carrying with him some baggage from his endeavours in the Second World War. Well, the key thing for our story is that on the top end of Explorer 1, James Van Allen had put a Geiger counter, basically, and the idea was you might detect a few cosmic rays here and there. And so it was launched successfully, and when they turned the instrument on, one of Van Allen's colleagues was observed to note that, my God, space is radioactive, because there were very high fluxes of electrically charged subatomic particles, so alpha particles and beta particles, if you like. And this had not been predicted. And we can look at then how Van Allen went on to develop this idea, and he moved on, and this is a schematic from the period, and we have the Van Allen radiation belts. So we have electrically charged particles, subatomic particles, which have become trapped by the Earth's magnetic field, and they form an inner and an outer belt around the Earth's magnetic equator. And they are known still to this day in many circles as the Van Allen radiation belts. If you go back through the history books, it looks like some of the earlier Soviet probes also discovered these things, but weren't published in quite the same timely fashion and not publicised as well. So we still know them as the Van Allen belts. And there is James Van Allen on the cover of Time magazine. So if we now step forward to sort of present day, we're well aware that the sun is a large volume of plasma containing most of the matter in the solar system, most of it at very high temperature. And here we have some observations from the Solar Dynamics Observatory looking at looking at the corona in a variety of temperatures between about 1 and 2 million Kelvin. And as you can probably tell, I'm not a solar physicist, and actually the solar physics content of this talk about space weather is relatively small. But the sun is the source of our space weather. And we can see here the takeaway message is that we now know the sun is not a uniform object in the sky. It's highly dynamic, highly structured, varying on timescales from seconds to years and centuries and probably longer. And so the sun is remarkably time dependent. The environment around the sun is also, therefore, remarkably time dependent. And you can see here the sun crackling with activity, much of which is being constrained by the sun's magnetic field. So you can see the loops and the arcades of magnetic field poking through the solar surface. And if we stand back a little bit and take a coronagraph image of the sun, and so to orient everyone who's not familiar looking at coronagraphs, what we're looking at here really is an artificial eclipse of the sun. This is actually quite an old movie now. This is from Soho, so it's about the time of the turn of the current century. And the sun is located in the centre of the movie, where the white circle is. And actually we have a disk put in front of the imager to create an artificial eclipse. And by doing that, we're able to use an instrument with sufficient sensitivity to see scattered or emitted lights from the region around the sun without obviously it being overloaded by the brightness of the sun itself. The stars are in the background, obviously, as the spacecraft is orbiting the Lagrangian point between the Earth and the Sun. So it orbits the Sun once a year, so the background star field is drifting, and the eagle-eyed amongst you will have noticed a planet creeping in there, and also a comet on its final dive into the Sun. But again, the thing to take away from this is this constant activity we see. The solar wind is continuously emerging from the Sun. So basically 24 hours a day, 7 days a week, the sun is churning out the solar wind into the solar system. So this is mainly ionized hydrogen, so protons and electrons, but also about 5% helium, nuclei, and then some traces of some other things. But basically, it's mainly hydrogen with a little bit of helium put in, all ionized to give us a plasma. So we have a mixture, an ionized gas of charge-carrying particles, some of them heavier than others. And this goes on all the time, so the sun is throwing out about 1 million tons per second of its outer atmosphere into the space environment, and this is material which is so hot that the sun's gravity can no longer hold on to it, and is also sitting on magnetic field lines which allow it to escape into the interplanetary environment. So that background activity is going on pretty much all the time, but as you can see from this movie as well, periodically there will be an explosion of solar material. So you can see them, they're sort of like puffs of smoke coming out. Those are, in fact, coronal mass ejections, so roughly 1 billion tons of plasma being ejected at roughly 1 million miles an hour in almost any direction throughout the solar system. And so space weather is continuously around us. The environment around our planet, being driven by solar activity, is constantly changing due to the changing solar wind. But also, it occasionally becomes very disturbed when bursts of activity that we can see here in terms of matter, coronal mass ejections are being fired out, but also solar flares, so very rapid intensifications of the radiation output of the sun, often in X-rays and extreme ultraviolet wavelengths. So our story then brings us a little bit closer to home. And so a few slides ago, I showed that image of the magnetosphere as pictured in the 1930s as well, it wasn't even a magnetosphere there. The Earth was simply an obstacle to solar wind flow. Well, the solar wind, if it is electrically charged, it will carry with it the sun's magnetic field, as we're going to get to in the next animation. So as the solar wind expands outwards from the sun, it brings with it the sun's magnetic field and drags it out into the solar system, where it becomes known as the interplanetary magnetic field. And so one of the pioneers thinking about how this would create interactions with the Earth's magnetic field was James Dungey, for whom this prize lecture is named. And this is a freehand sketch by Jim Dungey of his open magnetosphere from in the 1960s. What he's drawing here is a magnetic field line from the sun arriving at the Earth and then interacting through magnetic reconnection with the Earth's own magnetic field, setting up a cyclic flow. And I'll show this in a slightly updated version in just a moment. But there we have Jim Dungey on the left-hand side, shortly after his retirement from Imperial College London, holding aloft the gift he was given on retirement, which is his magnetospheric weather vane, which is absolutely splendid. And so, if we want to think about what those sketches were trying to show us, I've tried to cobble together an animation that would show you. So if we imagine the sun at the centre of the solar system with the solar wind continuously expanding outwards into the solar system and past the planets. Because it is a plasma, it's an electrically charged gas, it is electrically conductive. And so Maxwell's equations tell us that it will therefore drag the magnetic field of the sun out into the solar system as it moves outwards. So the magnetic field lines of the sun become stretched and as they move out, as the solar wind moves out through the solar system. So we can imagine a magnetic field line has to be stretched and pulled out into the solar system as the plasma, which is moving away from the sun, drags it outwards. Often analogies we use in teaching is it's a bit like the beads on a string, and it doesn't really matter whether you think, if you think of the plasma as the beads and the magnetic field as the string, it doesn't really matter if you think of moving the string and the beads follow it, or moving the beads and the string follows it. The field and the plasma, the string and the beads move together as they expand outwards through the solar system. Well, this can have an almost arbitrary orientation, polarity of magnetic field when it arrives at the Earth. So I've deliberately not put any arrows on that. But if you imagine at some point later, this isn't to scale, a magnetic field line which has come out from the sun will arrive at the day side of the Earth's magnetosphere. So the magnetosphere is simply the sphere of influence, the region of space dominated by the Earth's magnetic field. Well, if it has a southwards orientation, it will be oppositely directed to the Earth's northwards polarity magnetic field. And so the Earth's magnetic field, I should say, before I get too distracted here, the magnetosphere is formed basically because we have that rock in a river effect. The solar wind is continuously being diverted around the magnetized, the magnetic field of the Earth. Another consequence of Maxwell's equations and frozen in flow and some work done by Alfvén is that the magnetized plasma from the sun, in theory, does not mix with the magnetized plasma in the magnetosphere. The plasma in the magnetosphere mainly coming from the top of the Earth's atmosphere. And so we have two very distinct regions which don't generally mix. But when we have large spatial gradients in this in magnetic field, then actually the magnetic fields can reconnect, they can reconfigure or merge, as our colleagues on the other side of the Atlantic prefer to call it. And so if we look into that region, what we find is that a southwards pointing magnetic field in the interplanetary magnetic field, which is convecting along with the solar wind, will actually interact and reconnect with the Earth northward pointing field and peel it back, a bit like peeling back layers of an onion, if you like, or the skin of an onion. And that's because the magnetic field remains embedded in the solar wind. It continually moves in an anti-sunward direction, and the stretching of the field lines in the tail will actually set up another anti-parallel field line configuration when at some point they will reconnect again, and these field lines convect back round to the day side. And so a natural consequence of magnetic reconnection is that we get overall time average balanced, but at any moment independent reconnection processes going on the day side and on the night side of the Earth that set up the whole magnetosphere, stirs up the magnetosphere into a convective cycle. And this convective cycle is known as the Dungey Cycle, for the work of Jim Dungey, who predicted that these kind of interactions must occur. So why is this important for space weather? Well, we've got that same cartoon running on the top left hand of this particular slide. How does that impact upon the Earth? Well, these cartoons, I haven't oriented it, so I've committed the first lecturer's sin, but what we're doing is we're looking at the Earth in the noon-midnight meridian from dusk. Or, if you prefer it, we're looking at it side on, and North Pole is at the top and the South Pole is at the bottom. And so that's why the field line's going into the polar regions. Here is the view of the Earth from the same kind of perspective. We're looking at it side on, so we're in the equatorial plane looking at the Earth. If we tip that view over, what we find is that this motion of field lines over the pole from the day side to the night side reconnection site and then convection back at low latitude maps down into the upper atmosphere, and it sets up a flow of field lines and plasma in the upper atmosphere or in the ionosphere, which goes from the day side across the polar region. So as a field line comes in, the footprint of newly reconnected field lines gets dragged over the poles, reconnection goes on in the tail, and the newly closed the field lines convect back round to the day side, and this process continues. And here it is shown as being beautifully steady and ongoing, whereas in reality, of course, these day side and night side reconnection rates can be very different, and we can get all sorts of very interesting effects set up. But the takeaway message is that we have a stirring of electrically conductive material with magnetic fields moving through them. You're going to start getting electrical currents. And once you get especially into the collisional part of the upper atmosphere, the ionosphere, where it's partially ionized, so it's electrically conductive, the atmosphere is partially ionized by extreme ultraviolet light, breaking down the atmospheric constituents. It's not entirely ionized, so there's a collisional layer where neutral and charged parts of the atmosphere are able to collide with each other. What we get set up there is an anisotropic conductivity tensor. So the electrical conductivity of the atmosphere is not the same along the field line as it is across the field lines, and all sorts of interesting things start to happen. The main consequence of which is field lines, magnetic fields act as very good electrical conductors. Charged particles can move up and down them very easily, and so we actually get field line currents set up which flow into and out of the polar regions in the ionosphere. And to maintain electrical current continuity, we have to have closure of currents horizontally through the upper atmosphere of the Earth. And so our journey so far has really started at the sun. the movements of plasma and magnetic field out from the sun, and it brings us to the inevitable conclusion that certainly in the polar regions I've demonstrated here, we end up with motion of plasma and electrical currents flowing in the atmosphere a few hundred kilometers above our heads. Now that's a bit of a simplification, and geophysicists particularly like to make simple cartoons out of things, so here is a greater simplification of some of the interactions. Okay. It is a very complex process, and so what we were looking at a moment ago is electrical currents which were being, you can see there's a plasma flow, this sort of twin vortex pattern in the high latitude bit we were just looking at. And we were talking about particles moving into and out of the atmosphere. They don't just rain up and down the field lines, they spiral around them in a gyro motion. But there's all sorts of effects at mid and low latitudes as well, connecting the coupling the electrically charged and the electrically neutral parts of the atmosphere. So this will then link down to, and there are teleconnections that bring some of this energy down to very low levels as well, and there are implications for climate and a whole zoo of things which I'm not going to have time to discuss in detail today. But if we come back to nature's light show, if you view the northern lights from above, and this is the view from Tim Peake's office window in the International Space Station, then what you effectively are seeing here is when you see the northern lights, you can see usually structures rising up vertically or nearly vertically from the northern lights. You're seeing the footprints of magnetic field lines coming into the polar regions, and particles which are spiraling down them into the upper atmosphere are running into the atmosphere, causing it to glow. So we're simply painting the Earth's magnetic field with auroral precipitating particles and getting a light show as a consequence. And you can really get a feeling for these as you look over the horizon of how thin this layer of auroral emissions often is. And you can see it's beautiful, often there's structures in there which are really showing you enormous spatial variations in the amount of particles raining into the upper atmosphere. So you can think of this as a bit like a cathode ray tube. The electron gun is somewhere in the magnetosphere. It's a particle accelerator firing electrons into the upper atmosphere, and what we're doing is on the ground, we look up and sit underneath the screen looking at the scintillation, if you like, of the atmosphere above our heads. But it's not just the Earth that is impacted by space weather. If we look out into the solar system, and so here we have an image of comet Encke, and this was actually taken in 2007. So this is by the British-built heliospheric imagers on board NASA's STEREO spacecraft. Now, bear in mind, this heliospheric imager is meant to detect very faint levels of light coming from the solar wind particles, basically, so scattered light coming from the sun. And actually, it's an absolutely incredible bit of engineering. The sun is just off to the left of this, to the right of this frame, and this instrument has absolutely exquisite baffles to prevent stray light coming in, so it can see very faint features. And what you're looking at here, we have a comet Encke, which apparently visits the inner solar system every 3 years or so, with a nucleus about 5 kilometers in diameter. And then everything else you can see is the background star field. And this is actually a movie, and if I set it running, what you can see here is you can see Comet Encke moving through the frame with its tail, and then what will happen is, and it's just happened there, almost a vertical bar of slightly lighter region was going to move across the screen like that. And that's a region of slightly higher density of solar wind. So something has happened on the sun to emit a packet of solar wind which is slightly denser than the solar wind around it, and that has propagated across the comet. And when it comes in from right to left, you'll see actually it snips the tail off the comet there. And so there is a plasma tail on the comet, which itself will be magnetized. It will have its own induced magnetosphere as it runs through the solar wind. But this high density region comes along and changes the electrodynamics in the tail and snips off the comet's tail. Obviously, it grows a new one almost immediately. No comets were harmed in the making of this movie. But it's visible evidence, if ever it was needed, that space weather impacts things in the solar system. We can look out there and we can see it happening. And whilst we're in space, we can have a think about the most obvious consequences of space weather. As we approach the 50th anniversary of the Apollo moon landings, Apollo 11, during the entire epoch of the Apollo program, there were a number of solar energetic particle outbursts, which, had they washed over astronauts outside the protective region of the magnetosphere, and the Earth and the Moon spends most of its orbit outside the magnetosphere, then those would have given very serious radiation damage to the astronauts. So if you can imagine trying to land some of these spacecraft, suffering from radiation sickness, nausea, dizziness in 0G, and there were a couple of events which probably would have killed the astronauts outright. Now, at the time, that was not known about. These events were occurring randomly through the solar cycle almost, and the astronauts were, of course, only in space for a sort of a 3 or 4 day flight to the moon, on the moon, lunar surface for a couple of days, and then 3 or 4 days flight back. If you now try and map that forwards, thinking that we want to go to Mars, you're going to be in this environment for 6 months at a time, hoovering up every event that comes along. So space weather is going to have real serious implications for spaceflight if we have aspirations to go out beyond our own planet and explore the solar system. And whilst I'm on the subject of Mars, Mars is another example of what space weather can do. So if you're a planetary scientist, we look at Mars and it looks very different to the Earth now. Why does it look so different? Well, the problem is that Mars is just that little bit too small, so its heat of formation has probably bled away. The ratio of its surface area to its volume is such that it bleeds away its heat of formation and it's gone cold. And so unlike the Earth, which still has a lot of heat left over in it, and the churning of the nickel iron core in the planet generates a dynamo reaction and creates a strong magnetic field, Mars's magnetic field died away probably about 4 billion years ago. And so in the Earth's case, the rock in the river analogy, the rock is actually the Earth's magnetic field, and that shields the Earth's atmosphere and the surface from space weather. In Mars's case, the rock is the planet and its atmosphere, and so the solar wind can come down to very low altitudes and actually penetrate into the upper atmosphere and carry it off into the space environment. And so you get schematics like this drawn showing the loss of particles from the upper atmosphere of Mars. And that stripping of atmospheric material has been going on now for about 4 billion years, and so hence Mars has no atmosphere left. It's a cold, frigid, dry place. And so this long-term climate change on the planet is due to space weather impacting on the planetary environment. And to keep it newsworthy, if we think about it, this is MAVEN, which is one of the NASA fleets currently orbiting Mars, which is looking at the environmental change on Mars and is measuring this outflow, which is still going on today, from which you can start to make educated guesses about what sort of atmosphere Mars might have once had. This is the InSight lander, which landed on Mars a couple of weeks ago, and the whole purpose of that is to really probe the interior of Mars and to really see, has it got no tectonic activity? Is its core frozen and dead? It's going to measure temperature, heat coming out from the planets. It's going to look for signs of Mars quakes. So trying to understand how these planets have evolved in such different ways is a very hot topic, but is also very closely linked to space weather. And beyond our solar system, if we think about the kind of extrasolar planets that we're observing now throughout the universe, we have to think about, if we're looking for life, life clearly needs a long time to develop. It needs a stable environment to develop in. So again, on Earth, we have a multi-tiered defense field, if you like. The reason we're not all killed, or we're never evolved because of very high energy X-rays and ultraviolet light coming from the sun, is that our atmosphere absorbs the vast majority of it. Well, to keep the atmosphere, you need a magnetic field to shield the atmosphere from the solar wind. So we have a several-tier defense shield, if you like, that keeps the environment so close to the surface of our planet a good place, stable enough for life to develop. So if we're wanting to find life on some of these planets orbiting distant stars, then we have to start thinking about, are those planets likely to have strong magnetic fields that can protect them from the space weather of their nearest star? It looks like our own star is actually pretty benign. A lot of the stars we see out there from missions like Kepler actually look like they're a lot more active in terms of magnetic activity, massive sunspots on them. So it looks like, it's not just the Goldilocks zone, it's not just how warm it is and whether you can get liquid water. We probably need the kind of things that the kind of environment's going to give a strong magnetic field to give a stable surface environment for life to evolve. I quite like the idea as well that it may be a precondition of life that you have to have the Aurora Borealis on a planet as well. It seems to fit rather nicely. And if we think about Van Allen discovering the radiation belts 50-something or 60 years ago nearly, and bring that right up to date, we now know that the radiation belts are very dynamic. And so this is a simulation of radiation dynamics from data from the NASA Van Allen probes. And it's just showing over a few days, over a week-long period or so, how the radiation belts don't just sit there as a fixed torus around our planet. They swell and shrink. Particles are energized within them. They diffuse through them. They are lost to them. They are added to them from magnetospheric circulation. A very complex system. And they move around. And these actually have MeV, so mega electron volt electrons in them, so-called killer electrons, very high energy particles moving at a good fraction of the speed of light, trapped in the radiation belts around our planet. Well, if you do a quick juxtaposition of a model, a visualization of where the radiation belts are to a visualization of where geostationary orbit is around our planet, you see that the radiation belts and geostationary orbit aren't very far apart. This is a European Space Agency visualization. And what we're looking at here is a realistic distribution of satellites orbiting the Earth. They are obviously blown up in magnitude considerably so that you can see them. However, because otherwise you've got sort of satellites here the size of the sort of, the Arabian Peninsula, but never mind. It shows you this is geostationary orbit. So here are the satellites that are being used primarily for communication. But then the vast fleet of orbiting vehicles around our planet. And when the radiation belts become very engorged and full of high-energy particles, they swell and engulf, actually, geostationary orbit. So if you're designing a satellite, you have to think about, will it be able to withstand MEV killer electrons? What impacts will those kind of particle fluxes have upon the radiation belts? On the satellites. What else do we know from the beginning of the space age? Well, I pulled this down last night. So this is solar activity. So magnetic activity is characterized by sunspot number over the past 6 solar cycles. So we are here. And you can see at the beginning of the space age, solar activity actually seems to be considerably higher than it is now, and it's been broadly decreasing since the beginning of the space age. If we take a longer-term view of the solar cycle, and we look at that 11-year solar cycle in terms of its sunspot numbers at least, we can see this regular pulsing of magnetic activity on the sun. And what I want to do is I want to just go back a little bit and rewind a little bit from where we are up here in 2018 and go back and just talk briefly about an event that took place in 1859. Now, this is quite a famous event, and this is known as the Carrington Event. So this is quite important to the story of space weather. And so Richard Carrington was, on his marriage certificate, his occupation was simply written gentleman. So he was a gentleman astronomer, a secretary of the Royal Astronomical Society, and from what I understand, he was probably quite troublesome, so he probably would have made your life very difficult, President. But another fascinating life involving potential bigamy, murder, all sorts of interesting things. That's another sidebar lecture. However, he was a gentleman astronomer interested in making observations of the sun, and we owe a lot to Richard Carrington, because he really... At the time, there was a feeling that solar activity could not be linked to geomagnetic activity. There was no obvious visible link between the two. The magnetized solar wind was undiscovered at this point, and even Lord Kelvin said this was all nonsense. It was nothing to do with the sun. And boy, was he wrong. It turns out that the sun has a very clear effect on the Earth's atmosphere and its systems. So here we have an excerpt from the monthly notices of the Royal Astronomical Society from 1860, in which Richard Carrington begins... We don't write papers like this anymore, do we? Whilst engaged in the forenoon of Thursday, September the 1st, in taking my customary observations of the forms and positions of solar spots, he was sketching sunspots with a heliograph, when suddenly the room he was in brightened enormously. And what he was actually looking at was a visible flare occurring within the field of view of his instrument. He originally thought the housekeeper had come in and opened the blind and was about to tell her off for doing so and realised he was on his own and the light was coming from the instrument. So he immediately ran off to go and get the housekeeper to show her what was going on. And by the time he'd come back, it had all stopped. So there's a lesson for science there, is if you see something interesting, keep taking measurements. But here is his drawing of an enormous sunspot group he was seeing at the time. And so this was the first recorded observation of a white light solar flare. And it was actually also, some of this was also noticed by another astronomer, Richard Hodgson, and it was actually reported in the same issue of the monthly notices of the RAS. However, for some reason, it's never referred to as the Carrington-Hodgson event. It's always just the Carrington event. But he was at home at Red Hill in Surrey. Meanwhile, a little way away at Kew Observatory, we have here from the British Geological Survey archive, we have magnetograms, so the measurements of the Earth's magnetic field. And we're actually looking at the two components in the horizontal plane, so the north-south component of the Earth's magnetic field and the east-west component. And they're not running on the same time axis because the needles on the chart would crash into each other, so they're slightly offset on this chart. But at this particular time, this is basically a magnetic crotchet, and this event in one component is the same as this one in the other component. There is just a little offset in the logger. And what was happening there is X-rays and ultraviolet light released by this flare were arriving at the Earth alongside the visible light flare that Carrington would have observed. And they were tickling the upper atmosphere. They were ionizing the upper atmosphere, increasing the amount of charge carriers in the upper atmosphere, so breaking down more neutral atmosphere into electrons and ions, at which point it becomes more electrically conductive, so currents, stronger currents can flow through the upper atmosphere. So as the flare arrives, currents flowing through the upper atmosphere, naturally occurring currents, electrical currents, enhance. They themselves set up magnetic fields. If you think back to school physics, then you think about a current-carrying wire, a magnetic field is set up around it. Then beneath those currents on the ground, you get a magnetic disturbance as the disturbance field superimposes on the Earth's background magnetic field. And so that's what's going on here. This is the solar flare arriving. And it then died down again. But then the next day, just over 24 hours later, if I remember rightly, these instruments all go off the charts. And what Carrington didn't know at the time is at the same time as that flare, an enormous coronal mass ejection was emitted. And actually, it was probably a pair of coronal mass ejections, the first of which came straight to the Earth, sweeping everything in its way, all the solar wind being swept out of its way, leaving a nice empty path for a second enormous coronal mass ejection to come along and impact upon the Earth. And it was a real perfect storm, probably. The orientation of the magnetic field bundled up inside that coronal mass ejection was probably just right to really start massive amounts of reconnection going on, stripping away the Earth's magnetosphere. And so an enormous geomagnetic storm followed. And we know this because we don't have to rely upon ancient scripts talking about fighting dragons in the sky and legends and gods and walruses dancing in the sky. We can see contemporary accounts in the newspapers of observers seeing the Northern Lights. And so I do like this one, it is worth reading. So on the 9th of September the 1st, we were high up on the Rocky Mountains, sleeping in the open air. A little after midnight, we were awakened by the auroral lights so bright that one could easily read common print. And some of the party insisted that it was daylight and began the preparation of breakfast. The light continued until morning, varying in intensity in different parts of the heavens and slowly changing position. So if you think about that, these are travelling people who are used to sleeping outside. And so this would have been very unusual. And these people kind of knew when the sun was supposed to be coming up, it was breakfast time. And they were having a discussion over, actually, it must be morning, look, it's so bright. At the time, the sky over San Francisco turned red 3 nights running with the aurora. Gentlemen in New Orleans took advantage of the Northern Lights to go out shooting at night time because all the birds started rising from the trees, at which point they were blasted with shotguns. So there was lots of contemporary accounts. Sea captains in the Caribbean, near Cuba, could see the Northern Lights. Huge displays of Northern Lights. So this was a really enormous event. So it looks beautiful. But we're now into the era where it starts to have an impact on technology. And so here we have a conversation, which would have been done in Morse code, but I think everyone's probably pretty rusty, so I'll put it in clear text. So we have a conversation between the operators on the Boston to Portland telegraph line in the United States. And they've been complaining that the aurora seems to be interfering with their instrument, with their telegraph system. And so the Boston operator sends the message, please cut off your battery entirely from the line from 15 minutes. And the Portland operator replies, we'll do so, it is now disconnected. Let's just take a stop there. They've unplugged everything, and they're still talking to each other. And the Boston says, mine is disconnected, and we're working with the auroral currents. So they're aware that the aurora are out, and that it's inducing a current in the line, which is sufficient for them to be able to modulate with their Morse keys to send messages. How do you receive my writing? It's better than with our batteries on. Current comes and goes gradually. And so probably what was happening is the current was being induced in the line, and the direction of that current was changing due to changing electrodynamics in the upper atmosphere. And on occasions, it would be reinforcing the direction they were trying to push through the line with their battery, and on other occasions, it was going against it. So it worked better without it. So it's hard to imagine modern-day telecommunications working in quite this way, it has to be said. What's really happening? Well, we go back to the cartoon physics. We have an electrojet, an ionospheric current being induced flowing through the upper atmosphere due to our connectivity to the space environment. And around it, so that's what's shown in this red line in this cartoon, and around it is set up a magnetic field, which if you're on the ground, you sense. So if this current is fluctuating rapidly up and down, these magnetic fields are fluctuating. The magnetic fields imposed upon you on ground level, imposed upon the background magnetic field of the Earth, are fluctuating rapidly. The other way of thinking about it is that Ampere's law tells us that the fluctuating magnetic field at ground level will induce an electric field in the surface of the Earth, which will try and drive an electric current through the surface of the Earth. The surface of the Earth is not very electrically conductive, but if you have long copper lines, which are earthed at some point, they are, and those currents will try, instead of flowing through the surface of the Earth, will flow through your lines. And that's what we can see on the right-hand side. This is actually some data from a transformer, a power station transformer in Scandinavia. And what you can see here is several things, and I'll go through them quite quickly, but we basically here have a measurement of the Earth's magnetic field, the north-south components of the Earth's magnetic field, or at least how much it's varying. And this is the time derivative of that. So if this is the magnetic field, and this is showing how quickly it's varying. So you can see where there's a big change in the magnetic field, we get a big spike here because there's a big change going on. On that piece of equipment in this power grid, there was a monitor to detect geomagnetically induced currents leaking through the earth line from the transformer into the earth. And what you can see here quite clearly is when you get these big changes in the Earth's magnetic field being imposed upon from space, then you start to see big changes in the dB by dt, the fluctuation, the wobbliness of the Earth's magnetic field that's surrounding you. And as that's happening, you're getting currents being driven through your power grid. And so there's been an awful lot of work done on power grids, because if you think about this, what we're potentially saying is we now have power grids that span nations, span continents. If we were to have a Carrington level type event today pushing the electrical currents through this, the impact would be we'd be driving large quasi-direct currents through systems built for alternating current, and it effectively damages transformers which can overheat and die, basically. You can damage them, knock them out. And we're talking about those transformers you see near power stations and on industrial estates. The things are the size of a house, which if it goes wrong, you can't simply phone up and have a new one delivered the next day. There's a 4-year lead-in time, and there's only 3 companies in the world that make them. So if the UK lost a significant fraction of its power transformers in a particular region or nationally, it would be a big problem. And so, as you can imagine, people like National Grid think about this quite a bit. And a really extreme space weather event is probably going to be one of these black swan events. You don't see them coming, they're very rare, and when they hit, they have a big impact. And so you really need to think about space weather, extreme space weather, the really heavy stuff, the kind of thing that Richard Carrington observed 160 years ago nearly, as one of these high-impact, low-frequency events. So it's something like volcanic eruptions or the tsunamis or large earthquakes. Now, at this point, you can go in a couple of different directions on this tack. And one of them is very entertaining and scares the willies out of everyone. And so what we could do is we could look at everything that could possibly go wrong in the worst-case scenario. And that's a useful thing to do. But it's a bit snake oil salesman. So instead, it's worth us having a sober consideration of how space weather can impact upon us in our everyday life nowadays. And this is an ESA schematic, and the words are probably too small to see. All I really want people to take away from this is there are a variety of effects from spacecraft and astronauts orbiting the Earth right down to ground level that can impact our economy and our society. And it is therefore something which we need to think about. And so you may be surprised to learn, unless your bedtime reading is documents produced by the Cabinet Office, that if you go away and have a look at the National Risk Register of Civil Emergencies, the front cover looks like this. You can just Google National Risk Register of Civil Emergencies and it drops in immediately. You'll find that, well, this is a matrix showing the likelihood of an event occurring in the next 5 years and then the impact if it occurs on that axis. So things that are unlikely to happen and doesn't matter anyway down here. Sorry, these are things that are likely to happen. Let me get this the right way around. This is, okay, unlikely to happen and wouldn't have much effect. This is likely to happen and would have a big effect. And so we start worrying more as we go up that direction across the plot. And there is a key. It used to just have words in, but they've gone for funky little icons now. This first appeared and space weather first appeared in the Risk Register in 2012. And it's this thing up here. That's the solar system. Okay, and it's kind of alongside emerging infectious diseases, poor air quality, and heat waves. But you can see everything else is in it. This is pandemic flus, there's flooding, this is a factory exploding, there's all sorts of things in there that the government worries about. So, it makes sense that the government should worry about things. Probably lots of governments didn't worry about tsunami until one happened, and then suddenly, people will say, I know you're building hospitals and things, but you should have been spending money on tsunami warning systems. The day before it happened, that was a tough thing to sell. And so documents like this produced by the government actually have quite a lot of explanation of what space weather is. So this is really, I guess, intended for policymakers and industry to see what's going on. And so there are people out there thinking about this already. And we can learn an awful lot from non-space weather events. And coming from Lancaster University, I have an opportunity here to flag a slightly different kind of thing. So it probably means nothing to anyone who didn't live in the northwest, but in the first weekend of December 2015, Winter Storm Desmond brought an awful lot of rain to the northwest, to North Lancashire and Cumbria, about 200 millimetres in one night. And the river flowing through Lancaster, the River Lune, actually recorded a flow of 1,700 cubic metres of water per second, which is actually the highest flow of any river ever recorded in England. And it turns out that the Lancaster main substation is about 2 metres above the level of the river, and with a sizable flood defence, but it was inadequate. And that station was inundated. So you had a mains electricity station under 3 metres of water, and therefore the plug had to be pulled, and 61,000 properties in the city were turned off the grid. Now, actually, what was interesting there is it's annoying when you have a power failure, but the power didn't come back on for a couple of days. Okay, so you soon realise that all the cell phone masts stop after about 6 hours because their battery backups go. And you think, oh, it's okay, I'll use the phone line at home. Most of you probably haven't got a phone that plugs into the wall. You might have a base station that plugs into a wall with a cordless handset, but that needs the mains electricity to work. So unless you know where your original phone that you can plug in a wall is, you're not going to have a phone. But lots of other things stop happening as well. And here you can see actually what happened there was 75 diesel generators. These are articulated lorry-sized things, had to be brought into Lancaster. And for the best part of the week, Lancaster City, 70,000 residences, properties were diesel-powered. Now, you can do that with a small city like Lancaster. Those were brought in from Scotland, Northern Ireland, all over the UK. But if that happened to Manchester or London or the South East or the UK, that would be a much different story. So there are all sorts of things you can learn from non-space weather events that you then have to think, well, how would it work if this scaled up a bit differently? Certainly, I suspect there's some university academics in the room. There's probably some of the middle management people of universities now, which I guess is what I am as well. There's an interesting thing here is that, so Lancaster University has about 12,000 students. 7,000 of them live on campus. So 7,000 students in one place with no power. And during the 1984-85 miners' strike, when the government cut back on electricity and generation and introduced rolling blackouts, students stayed in their rooms and used candles. Since then, health and safety standards have moved on. So just to give a little idea, you've got 7,000 people living in 6-storey buildings with no fire systems, no lighting, no heating, no provision to cook, flush, use running water of any kind. What do you do with them? You know, so when those university people in the room, when their administrators come around and say, how's your resilience plan looking? That's when you need it, okay? So actually getting these people away is tricky because the trains couldn't stop at Lancaster Station because there was no power at the station. So, you know, there's all sorts of interesting things we can learn that might apply to space weather from non-space weather events. But we've also got big gaps in our understanding of the space physics. And so, you know, there are groups up and down the country who, you know, Southampton, Leicester, Aberystwyth, Lancaster, exploiting, and the British Antarctic Survey exploiting things like the IceCat radar on Svalbard to probe the upper atmosphere. The groups at the British Antarctic Survey, Leicester and myself, run radar systems to probe the upper atmosphere. This is my radar in Iceland, which looks at flow in the upper atmosphere. And what they do is they give us measurements. So we've got just a couple of top-down views of the Earth here. The one on the left is showing data from magnetometers dotted around the surface of the Earth. Cheap, inexpensive instruments, the sort of Stephenson screen of the space weather world, if you like. Little windsocks showing the intensity and direction of currents in the ionosphere. Whereas on the right-hand side, we actually have a visualization of data from the SuperDARN radar network, which is multiple radars around the globe, showing us that twin cell convection pattern of stirring of the ionosphere by interactions with the space environment. Looks nothing like a twin cell convection pattern most of the time, because Mother Nature is much more complicated than cartoon physics. So there's a considerable amount of ground-based infrastructure to do to look at space weather. But also, we really need to understand the modelling. If we're going to do forecasting and be able to tell power companies and train companies and whoever what's coming, we need to think a bit more about the forecasting. And so there's a chain of modelling starting in the photosphere and going all the way down to the upper atmosphere that needs to be understood. And there are modellers in this room now and thinking about the radiation belts. So we've got groups at Reading, British Antarctic Survey, thinking about the modelling of these environments at Imperial College London, Mullard Space Science Laboratory. So, and you know, using models like the NOAA Space Weather Prediction Centre's NNIL model, which has now been mirrored in the UK at the Met Office's Space Weather Operations Centre. So there's an awful lot of UK activity in actually trying to move us ahead there. And even some fields you would think that aren't at all vulnerable to space weather really are. I mean, you can get these kind of graphics, and they always show the things you'd expect. You know, humans are going to be impacted by it, and satellites are. But one that's not in here are trains. So, you know, at the Carrington Event, in my part of the world, in the northwest of the UK, this was the state-of-the-art technology, and it was space weather proof. It was iron and steel and coal and oil and water and wood, and it didn't care. If you fast forward 160 years, I came down on a train that looked a bit like that today. Other franchises are available. But if you look at what's going on here, it's taking in power from the mains grid. If the mains grid goes, the train stops. We also have comms on board, radio communications that are impacted, many GPS-based systems on board. Believe it or not, there are some trains in the country that you need GPS to know which doors to lock or unlock when you get to the station. And if the GPS goes, they fail safe and just someone has to come and override them. So the guard has to go and unlock them one at a time. You know, the impacts of these things, they're ubiquitous, built into everything we do, and it could go. So we need to think about that. And even the track, we rely upon electrical currents flowing through the track to control signalling. Since Victorian times, electrical currents flowing through the rails short circuit as a train goes across, which de-energizes the relay and switches the signal to red. It's a fail-safe system. If you start inducing a current in one of these tracks that's got enough current in it to energize the relay, you can actually, it'll have a wrong side failure and it will fail on green. So there are all sorts of interesting things. Now, a train operating company probably isn't thinking about space weather. They're probably not as engaged as, say, a satellite operator or a power grid operator. Nevertheless, they will have some emergency business continuity plans that could apply. So here we have an instance of a train which stopped somewhere outside Lewisham Station because of some snow. And what you see is, after a couple of hours, you can't keep the passengers on the train. They get off. And that's because, you know, if you have a train that's lost power and stranded somewhere, then what happens is the system will start to shed load, it will turn off the air conditioning, the lights, and then the toilets, and all these kind of things. And people, you know, the environment inside gets horrible, and people get out. You know, you can't stop them after a while. And you see what's happening here is they're being escorted away, but there's emergency services are here to help them do that, because having people wandering around on a track, especially a track which might be having 20 amps of current being induced because of a space weather event in it, is a very dangerous thing. So actually, you're relying upon the business continuity plans might rely upon the emergency services turning up. Well, if the southeast goes out because of space weather, the emergency services aren't going to come and do this. They're going to be, you know, they'll be dealing with other things. And so actually, what we find is, like so many things, it's not one problem that's going to cause a headache. It's when you get several failures coming together. That's generally when you start getting, you know, disasters or big problems. So taking existing business continuity plans and adjusting them is probably the name of the game. And I'm going to wrap up now just to say things are subtly changing. Depending on what kind of North Pole you're interested in, the North Pole is wandering around a little bit. And that means over hundreds of years, our geomagnetic latitude has changed. I've got a lovely plot here from Mike Lockwood from Reading showing observations of the aurora from the UK since about 1650. And actually, the UK was probably a much better place to see the aurora in 1750 than it is today, because it was at a better magnetic latitude relative to the auroral oval. And so our geomagnetic risk has changed. And I'm just going to flag that some of my own work at Lancaster I'm doing with my team at the moment on an ERC-funded project. We're looking at those extremes in magnetic variability from decades of data sets and seeing what we can learn about those. And what we learn is, what these graphs are basically showing us is that the very biggest extreme variations in space weather have a latitudinal dependence, and it looks like, and so you get the biggest wobbles at around the edge of the Arctic Circle and the auroral oval. But that position is going to move over time. And so we need to think a little bit about how we're going to explore changes in the Earth's magnetic field. We've got some other plots we can talk about which show how the recurrence rate of the most extreme magnetic fluctuations we see, how that changes with latitude. And sure enough, you know, you can do what is the return period what is a typical level of disturbance you see for like 1 in 20 year return period or 1 in 200 year return period. And what it's telling you is that about the 1 in 200 year level, the Earth's field can fluctuate at about 3, 4, 5,000 nanoteslas per minute. And that's, if the Earth's magnetic field is about 40,000 nanotesla, you can see you could erode away about 10% of the Earth's field in 1 minute from very large geomagnetic disturbances, and that will create big currents. And just finally, something to think about is the timescales we're talking about changes to. They sound quite long. If you're in the game of building new build nuclear power station, then the risks you tend to worry about are 1 in 10,000 years. You want to know what the worst earthquake a site is going to have once every 10,000 years and the worst tidal wave that will hit a site every once in 10,000 years. And now they want to know what's the worst space weather that can occur once every 10,000 years. So there's all sorts of challenges ahead trying to unpick that rather beautiful cartoon. Thank you very much.
Jim, thank you very much indeed. We did actually ask you here to cheer us up, but, well, anyway, time for a few questions. Yes, please.
Hi. Can you hear me? Okay. Well, thank you for the talk. It's fantastic. I missed the beginning, so if you said this at the beginning, apologies. So my passion is chasing the aurora. And one thing that I always look at is, predictions of coronal holes, coronal mass ejections, so on. One thing it seems is not really possible to predict is the polarity of the solar wind. Is that something we might look forward to in the future? Or say, okay, there's a coronal hole opening up. Oh, and it has a nice southward component.
So that would be nice if we could do it. So the question refers to the fact that as a coronal mass ejection, for example, is fired out from the sun, it's hurtling towards the Earth. Depending on the relative orientation of the magnetic field bundled up inside that, relative to the Earth's magnetic field, could mean it could be very geo-effective or not at all geo-effective. So it could have a big impact or not. And trying to measure that remotely, we can do it in situ. So as that thing flies over a spacecraft between the Earth and the Sun, we can measure it with magnetometers on board. But those typically give us 30 minutes flight time, so we get 30 minutes warning. And really, Mr. President, we have to turn off the power grid or something, you've got 30 minutes, is not very helpful. And really, the power companies would like, 4 weeks' notice. Well, we're not going to get that either, but several days is useful. So trying to predict that polarity of magnetic field inside a coronal mass ejection is, in theory, possible. There are some physical phenomena you could do to remote sense that, but we're not nowhere near there yet to do it practically. Okay. But it is a kind of holy grail of forecasting.
Another one question we've got time for. Kathy Whaler in the middle.
Thanks very much. I also missed the start of your talk, I'm afraid, so apologies again if you talked about this, but you've concentrated understandably on the extreme events, but there are insidious, continuing degradation of the insulation of power, systems and damage to satellite chips and things like that. Which do you think is the thing that we should concentrate on?
Is it an either-or question?
Well, I don't know. That's another important thing to.
It's hard to say because trying to quantify the damage of some of these things, and at the end of the day, it's going to be money that talks. How much is it going to cost, to replace a transformer? How much of the lifetime does it do erode away from it? So we've seen examples in recent years where there have been events which haven't been large enough to damage a transformer, but over a course of months, when the sun was particularly active in 2003, there were several transformers that kind of slowly went downhill, and then had to be taken out of service. So there is definitely a cost to that. I'm guessing that is the sort of thing you could probably more easily fit inside a business continuity plan, that you'd have to keep checking and fixing these things. But I think it's very industry specific as well. I think, if you've got some sectors like the rail sector where they've got huge problems with just regular weather or terrorism or leaves on the line or whatever it is, it's quite hard to push this stuff into any of the top 10 things they need to worry about, and it would be something big they would worry about, I think. So I don't think there's a one-size-fits-all.
Okay, let's thank Jim again for an excellent Dungey lecture. Well done.